All right, so we've talked about motion in one dimension, we've done kinematics problems in one dimension, now we're going to move into two dimensions. So we're going to do it all over again, but with two dimensions. So we have the same aspects, right? The same idea. We still have position, we still have velocity, we still have acceleration. These are still the same concepts, but instead of an object moving in just the x direction or just the y direction, this object is going to be moving off at an angle. So we're going to have to break things down, like the velocity and the acceleration, into their x components and their y components. And we have to do this because motion in the x direction and motion in the y direction are calculated completely independent of each other. So an example of this is going to be projectile motion, right? So let's say we have a person that is standing on top of a building, and instead of just taking the ball and dropping it straight down, they now are going to toss the ball up at an angle, right? So this object is going to trace out a path that's in the shape of a parabola. So this object is not only moving in the x direction, it is also going to be moving in the y direction. So we have to figure out how to represent this, how to determine the velocity and acceleration. All right, so this simulator is a great way for us to look at how velocity changes throughout the motion of 2D projectile motion, right? So if I have this cannon, I shoot a cannonball out, we can see that this object moves in the shape of a parabola, and what we are being shown here, this arrow, is the total velocity vector of this object as it moves through the parabolic motion. So if I change the angle that this cannonball leaves the cannon, it changes things like the maximum height as well as the range, or how far this cannonball travels. So when I'm thinking about projectile motion, I like to draw a picture of the motion of this object, and there's a few different things we want to think about. We want to think about the velocity vector, we want to think about the x and y components of that, and we also want to think about the acceleration, right? So I'm going to put a couple key points on this path, and we will talk about what happens throughout the motion of this object, right? So we had the total velocity of this object, which is pretty much going to follow the actual path that has been traced out. So this is going to be my total velocity. So now I can break this down into the x and y components. So to do this, we're going to do right triangles, right? So the x component of the velocity is going to be in yellow, and I'm going to put my y component in this blue color. And one thing that you notice here is that the x velocity, or the velocity in the x direction, has the same directionality throughout the entire motion of this object. But the velocity in the y direction changes, right? At the beginning, it's going up. At the end, it is pointing downwards. And at the maximum height, it is not appearing. Why is that? So we can see that the components of the velocity change throughout the motion of this object. So I'll slow this down a little bit. We have the y component that changes directionality and magnitude throughout the entire path, but the x direction keeps the same direction and magnitude throughout, right? And this has to do with the only acceleration acting on the object is coming from gravity, right? So the acceleration due to gravity is pointing down the entire time. There is no acceleration in the x direction. This is because there's no forces acting in the x direction. We haven't gotten to forces yet. I think the best physics textbooks actually introduce force and then come into kinematics because it's a little bit confusing, like why we have one force but we don't have like an x direction, and it's hard to explain without saying it's because we don't have a force in the x direction. The only acceleration that happens is in the y direction. So this means, right, if we have an acceleration, we have a change in velocity. If we do not have acceleration, we do not have a change in velocity. So what this tells us is that my velocity in the x direction, or the x component of the velocity, is not going to change at all throughout the entire process. So I know that if I consider this, let's call this position, let's change the color. That's not a good color either. Position 1, 2, 3, 4, and 5, right? I know that my velocity in the x direction at position 1 has to be equal to the velocity in the x direction at 2, has to be equal to the velocity in the x direction at 3, etc., etc. So recall that our acceleration is equal to a change in velocity over a change in time. If my acceleration is 0, this means that my numerator has to be 0. There is no change in velocity. This velocity has to be the same throughout the entire process. So that tells me that if this is my initial position, and let's call the top my final position, my velocity initial in the x direction has to be equal to my velocity final in the x direction, right? This is, well, technically it's not a vector because I have already taken the x and y components out of it. This tells me that I don't have a changing velocity in the x direction. Fantastic. Now, what about the y direction, right? We know that because we have an acceleration due to gravity, that my velocity in the y direction is going to be changing throughout this process. So one thing that is important to note is that at the top of motion, right, at the max height, my velocity in the y direction is going to be equal to 0. So the x direction has the same directionality and magnitude throughout the entire process. What about the y direction, right? We see that this y direction initially is pointing upwards, then it starts to point downwards. We also see that the magnitude of the y component of the velocity changes throughout this process. And this is because in the beginning, my acceleration is opposing the direction of motion, right? So it is slowing down. On the second half, my object is now speeding up in the negative direction. So my acceleration is pointing in the opposite direction of the velocity y component. And as this moves, this causes the magnitude of the y direction to become smaller and smaller until it hits max height when the y component of the velocity is going to be 0. This is because it's now changing directionality, right? So if we allow it to keep going, we see that the y component starts to get larger and larger. This is because the acceleration in the y direction is causing this to accelerate in the negative direction. So what does this tell me? This tells me that at the max height, my velocity in the y direction has to be equal to 0. It has to be equal to 0 at max height because there's no vector here, right? So I can write that the final velocity in the y direction is equal to 0, right? Because this is my final in this layout. I can also go ahead and write down that my acceleration in the y direction is negative 9.81 meters per second squared. And what about that x direction, right? Well, we have no acceleration in the x direction, so it's going to be 0. What else can we see about this? Well, we can also see that our angle is going to dictate not only how high this object goes, but how far or what the range of this is, right? So at 45 degrees, I'm actually going to get, let me get rid of the vectors here. I will get the max range. So let's figure out where that's at. My max range for this setup is going to be about 26 meters, right? So if I increase it just a little bit to 50, we see that this object goes higher, right? It has a greater max height, but it doesn't go quite as far. And if I decrease it to 40, the object is going to have a shorter max height, but it's also not going to go as far. 45 gives me my maximum range. We can also see that certain angles will produce the exact same range, but they'll have different heights. So a great example of this is 30 degrees. If I shoot this object from 30-degree angle, and I also shoot this from a 60-degree angle, these paths, these trajectories are very, very different, but the total range is going to be the same. And what's interesting is one is going to take significantly longer than the other. So at time of 1 second, the 60-degree is at 8 meters, and at 1 second, the one that I shot at a 30-degree angle is at 13 meters, right? So that's because the one at 60 degrees has a further path that it needs to travel, right? Because it has a max height of roughly 10 meters, whereas this one is like 3. And we see that this occurs with a variety of different angles, right? So if I go to 65, and I also go to 25, these should give me the exact same range, but drastically different heights. It takes a different amount of time. They have different paths that they trace out. So how do we solve these problems? We solve these problems, right, any sort of projectile motion problem, still using the kinematic equations. But now our kinematic equations are broken into the x direction and the y direction. And you'll notice here that the equations that are in the x direction have no y components, right? These are all x. And the ones that are in the y direction are all y. We cannot put an x component into a y kinematic equation. So we have to calculate the x direction all by itself, and we have to calculate the y direction all by itself. Why? Well, because, for example, we have acceleration in the x direction here, but acceleration in the y direction in the other equations. And we know that, for example, in our parabolic path, we have an acceleration in the y direction of negative 9.81, but an acceleration in the x direction of 0. Another thing that I think is important to note here is how do we connect these together? A lot of problems, especially 2D kinematics problems, 2D motion, projectile motion, is where we start to see systems of equations, right? Where you have two equations and two unknowns, you have to combine them together to find the answer. So how do I connect the x direction and the y direction together? I do this through time, right? Time is its own dimension. It is not an x or a y component. So I can connect the x motion and the y motion together through time. So there are a few main things that I want to really point out, explicitly state for projectile motion problems. Things that are important to recall, etc. And those are that when we have projectile motion, my initial velocity in the x direction has to be equal to my final velocity in the x direction. This is a really important thing to remember because it can help simplify problems a lot. The other one that I want you to remember is that if we have projectile motion and we throw an object, this object is only acting with gravity involved, my acceleration in the x direction is going to be 0. Which means my acceleration in the y direction is negative 9.81. Right? These are important to remember. The other thing that is important to remember is that at max height, my velocity in the y direction is 0. This is because my velocity vector has to change positions, right? So if I plot out my position as a function of time, right? This is y is equal to 0. So this object is going to go up, and then it is going to come back down. I know that the slope of this line is going to be my velocity. So at this top point, my slope is equal to 0. This means that my velocity is equal to 0. I also see that the slope on the left-hand side is positive. The slope on the right-hand side is negative, meaning that I am changing directionality here. I can also plot out the velocity as a function of time. And this one I think trips people up a little bit, right? Because this object is going to be slowing down. Let's do it this way. So for the first half, my object is going to be slowing down in the positive direction. And for the right half, this object is going to be speeding up in the negative direction. This means that at time is equal to 0, I'm going to have a very large positive velocity. And up until, let's call this where max height occurs, this object is going to be slowing down, but still in the positive direction. All of these velocities here are still positive values. They're just getting smaller, right? Then it is going to start speeding up. Oh, that's a bad line. It is going to start speeding up in the negative direction, right? So we now have negative velocities that are getting greater. In order for us to cross from a positive velocity to a negative velocity, we have to cross this v is equal to 0. Keep in mind this is all y directionality only, right? The x is just straight line the whole time. So a few common areas of confusion that students have. The first one is thinking that for certain setups, the initial velocity is 0. So the best example of this is there are problems where they're like, there is a guy and he has, or a lady, and they're throwing a football. Figure out, I don't know, how far the football goes. So people assume that because whenever an object is dropped, that the fact that it's in our hand is what's dictating that the initial velocity is 0, and that's not the case. It's because this object is starting at rest and I'm letting go of it and it starts to speed up in the negative direction. So they take that concept of this object is in my hand and I'm letting go of it, and they also apply it to this football situation, and they think because when the person is throwing the football is in their hand, this object has an initial velocity of 0, and that is not the case. So we need to think about this like the moment that the football leaves this person's hand, what is the velocity? So we want the initial velocity to be the moment that this object has left this person's hand. And at that point in time, the initial velocity is not going to be zero. It's going to have some velocity to it. So don't be one of the people that gets stuck in that trap thinking because the person is holding on to the ball, the initial velocity is zero. No, it is the second that this object leaves the person's hand that our initial velocity is calculated. So why? Because the initial velocity would be considered the moment the object is released. When would our initial velocity be zero? If an object is dropped from rest. That's the only point in time. So, problem solving for 2D kinematics problems. Make sure you read the whole problem, draw a diagram, and list out your axes. I think it's really helpful I always go back to this person standing on a building, right? Let's say projectile motion. I personally think it is helpful to always draw somewhere your X and Y axis so that it's clearly visible next to your picture. The other thing, list out have, want, and need and break it into the X and Y direction immediately. Oftentimes it'll say, Billy Bob releases a ball and throws this ball at a 30-degree angle above the horizontal. So your horizontal, if this is ground level, it just kind of translates up. So the horizontal is going to be this horizontal line coming out from this person's hand, 30 degrees above the horizontal at a speed, it'll often give you speed of like 2 meters per second. Figure out how far away this lands on the ground. Well, the very first thing that I would do in this situation is I would say, okay, it gave me a magnitude of velocity, it gave me a directionality, but because my kinematic equations are in an x component and a y component, I have an x direction, I have a y direction, I need to break this down into the x and y directions immediately. And to do that, I need to do my trig right triangles and find the x component and the y component. So I would do that before I even start trying to solve the problem as I'm listing out my have, wants, and needs for this problem. As always, figure out the physics you need to use, which equations are going to be the best for the problem, solve the algebra, plug in numbers, and does it seem reasonable? Make sure you also check your directionality with these projectile motion problems. This is a common area of mistake that'll mess the whole thing up.